So, welcome to this session exploring technical and customer data for improved products. We have 5 papers today. In particular, we have one that is presented by Iryna Mozgova, whose title is Knowledge Annotation within Research Data Management System for Oxygen-Free Production Technologies. Iryna is from the Institute of Product Development of the Leibniz University at Hannover. Then the second paper is instead from Shuo Yang, and here we have a paper whose title is Patent Data for Engineering Design and Review. And the presenter is a student that was visiting PhD at the Massachusetts Institute of Technologies for 1 year. Then he was also visiting at the Innovation Lab at the Singapore University of Technology and Design. His research interests include data-driven design, machine learning-based engineering design, and computational design methods. Then we have a third paper whose title is Patent KG, Patent Knowledge Graph Extraction for Engineering Design. It is from Wanzhao Zi, he is a PhD candidate at the Dyson School of Engineering Design at the Imperial College in London. Then we have a fourth paper whose title is Information Retrieval and Server Design for Two-State Customer Preference Modeling. It is from Yinshuang, Xiao, and Z forse, sorry. It is he is a student and graduate research assistant in the Walker Department of Mechanical Engineering at University of Texas at Austin. And then the last paper is from Maurice Meyer. It is on planning the analysis of use phase data in product planning. Maurice Meyer works at the moment at the Advanced System Engineering Research Group at the Paderborn University. So I think that we can start with the presentation. So first we will have all the 5 presentation, then we can have a discussion all together, so we can have the questions and the answers. I don't know, Yelena, if you can start the presentation.
Welcome to the presentation, Knowledge Annotation within a Research Data Management System for Oxygen-Free Production Technologies. This work was carried out within the scope of the Collaborative Research Center 1368, Oxygen-Free Production. My name is Iryna Mozgova, and this is our team with authors from the Institute of Product Development, Leibniz University, Hanover, and the Leibniz Information Center for Science and Technology, University Library. Let me start with the background of our project. The production processes of the metalworking industry from the very beginning until today are usually carried out in the presence of oxygen that is usually in a natural air atmosphere. Oxidation acts predominantly as a disturbance factor in different production processes. We can observe, for example, defects, oxide skins, oxidation of tools and components, or pore formation. The research objective of the project is to develop new oxygen-free production processes, and the possible solution involve understanding the processes in a joining zone and technology that completely removes oxygen from a process zone. The project includes 15 sub-projects grouped into 3 main research areas, as well as a project carrying out central analysis. All of these projects produce different heterogeneous research data that ranges from measurement data, observational data, data from simulation to image and videos. To deal with this data, it is necessary to create an approach and a system that takes into account the interests and objectives of all stakeholders in the project. In other words, a research data management approach is required. This is what our team is aiming to provide. In developing the data management approach, several challenges were identified. How to implement intuitive research data management tools to support research data processing between different projects or in collaborative projects. How can the process of documenting and monitoring measurements of research objects between sub-projects be organized? How can data in research data management systems be interlinked with each other in order to generate new findings? The concept we have chosen is the following. The first step is to identify project-specific research data and workflows and to understand the structure of protocols and reports. To eliminate the inhomogeneity of the identified data structure, it is necessary to determine the respective metadata and establish a relationship by using a domain-specific vocabulary. The next level is a research data management system, including a data management system to store raw data and a knowledge management system to support the storage of protocols. The two main parts are realized using the open source software Secant and Semantic Media Wiki. The system may be semantically linked. Here, the organization and data quality control include input, search, and report functions, as well as the monitoring of central analytics processes, for which we develop a measurement request system. The central service project Central Analytics from the Technical University Clausthal analyzes and describes the surfaces and interfaces investigated in the sub-projects in the CRC. The objectives here are to establish and provide a central analytics infrastructure, to carry out a uniform analysis of surfaces and interfaces, and to support the sub-projects in their specific research of surface and interface processes. In order to achieve these objectives, it is necessary to realize an oxygen-free transport and transfer of samples between the central analytics project and another sub-projects, as well as planning, coordination, and implementation of surface and interface analytical investigations, which is implemented in the framework of the so-called measurement request system. During the development of the system, the requirements of the users were collected, data and activity workflows were also analyzed. The former process of measurement request was based on PDF forms that were emailed by the researcher requesting to investigate a specimen to the researcher responsible for making the measurement. During the development, we identified key request-relevant objects and their characteristics. Some of those are depicted in this slide. Key request-relevant objects are implemented in the Secant-based data management system and in the Semantic Media Wiki-based knowledge management system. You can see that the objects are semantically linked to each other, which allows to implementation of different queries and provides a flexibility of the system for different stakeholders. The developed system makes it possible to structure information flows and data exchange processes between sub-projects, to link data and research protocols, and to record and monitor the location and status of samples. On the right-hand side, you can see a screenshot of the request template in the system, as well as a part of a screenshot with the requests saved in the system. The presented approach allows to store research data in the data management system, research protocols in the knowledge management system, and semantic linking of systems using a domain-specific vocabulary. The monitoring of the status of research objects is implemented via a measurement request system. The presented approach can be generalized and mapped to other research domains. Thank you for your attention.
Hello everyone, my name is Jiang from Shanghai Jiao Tong University. I'm very honored to be here to share our paper today. In this paper, we conduct a systematic literature review to present the state of the art of patent data for engineering design. The whole presentation are made of 5 parts. Let's begin with the background. Mining patent data to develop design theory and methodology has a long history and can be dated back to 1950s. Altschuler and his team developed the theory of inventive problem solving by manually reviewing and analyzing thousands of patent documents. Recently, advancements in artificial intelligence and data science present a growing opportunity to mine big patent databases in design research and practice. Specifically, patent for design research has experienced 3 phases, from the early expert-involved methods like trees to recent data science and AI-based methods. As we all know, latest AI technologies normally require big data for training and testing use. Thus, patent databases are ideal data source to leverage up-to-date data science technologies for engineering design research. Let me take United States patent document as an example. The United States patent data contains 5 parts, including bibliometric information, text, image, classification information, and citation information. There are mainly 3 advantages of using patent documents as databases for engineering design research. First, patent databases are natural large-scale repositories that accumulate over time as inventors file patent applications for their inventions. Second, patents contain massive design information on technologies, systems, or processes from all domains in both textual and visual forms. Moreover, every patent is assigned to one or more patent domain classes by examiners, which making patent data ready for supervised machine learning applications. Let's go to our literature retrieval methodology. Our literature retrieval methodology includes 4 steps. In the first step, we searched in Web of Science in the range of 8 leading engineering design journals with a query, which identifying 32 papers. These journals including ASME, JMD, JScience, Research in Engineering Design, Journal of Engineering Design, Design Studies, Design Science, AIDEM, and CAD. Then in step 2 to step 4, we fine-tuned our results. The final literature pool has 58 papers. This paper presents the distribution of these retrieved papers by publication year, journals, and keyword or co-occurrence. We can see a clear growing trend in figure A. Let's go to part 3, review and analysis of the field. As we review the patent for design literature, it becomes clear that patent data have been utilized to advance these 4 topics, including design theory, design methodology, design tool, and design strategy. We manually classified retrieved literature into each of 4 categories. This figure presents the proportion and categorical distribution. We can see most of the patent for design literature focus on design methodology. Then we reviewed all the retrieved 58 papers in detail. Because of the time limitation, we cannot summarize this content one by one. You may check our paper for more details about them. This figure presents a visual summary of the algorithm and the data parts of existing patent for design studies and the coupling of the 2 dimensions. One research may adopt multiple methods on multiple data sources. The different line color denotes different data parts of patent documents. Next, we discuss and propose several future directions based on the analysis of the field. We discuss future opportunities in the view of data, algorithm, and application. For data, patent databases are natural benchmark datasets for supervised machine learning applications because every patent is rigorously labeled by patent office about its technology domain. The second, patent texts constitute a heavy load of design information that can be used for creating datasets for NLP-related tasks, such as entity recognition and the detailed analysis of functions, behaviors, and structures of engineering designs. It is recommended that researchers utilize multimodal pattern information instead of a single modality. For algorithm, engineering design researchers may adopt or adapt deep learning methods developed in computer science literature for patent prior art search, design classification, and design representation. Then, graph neural networks enable us to extract relational information among patterns and derive high-dimensional representations for downstream tasks, such as design repository restructuring and design stimuli identification. Also, various machine creation studies in computer science field, including text and image generation based on deep generative models or large pre-trained language models, can be utilized to develop design generation methods. Last, for application in design science and strategy research at higher levels are limited. Statistics of the big multimodal pattern data can substantially deepen and further our fundamental understanding of design team science, designer behaviors, and regionals, design impact dynamics, and so on. Although several design tools have been developed based on corresponding design methodologies, only a few of them are open source and can be directly used by engineering designers or researchers. So we recommend the researchers to open their developed tools with a user guide, such as uploading the code on GitHub. Finally, let me make a conclusion. We contribute to the literature by illustrating the state-of-the-art pattern for design studies and identifying new and feasible future research opportunities. Our structured review of the data, algorithms, and applications of existing pattern for design research, providing a foundation and basis for researchers to follow the relevant latest efforts in a coherent form. Several research directions are proposed in terms of data, algorithms, and applications, respectively, to bridge the gap between the pattern data mining and engineering design research. That's all. Thanks for your listening.
Thank you, everyone. Thank you for attending my presentation about pattern knowledge graph extraction for engineering design. So the background is that a scientific discovery can be established by systematically studying the existing knowledge. Reusing existing knowledge to speed up the idea generation has already been used in some domains, such as design. So we are interested in the knowledge in patterns because patterns are a kind of documents recording the content of inventions and containing a large number of scientific and technological knowledge. This sounds perfect and very tempting, but there is a very serious problem. The patterns are characterized by long description synthesis and complex structure, also very professional and legal terms, which make it very hard for a layperson to read and analyze. The existing two methods, rule-based extraction and neural network-based extraction, both got their own limitations. For example, listing the rules are very laborious, and we don't have annotated data to train the neural network. So this gives us a question, how to extract the knowledge. So the Horizon Pattern KG approach proposes a new unsupervised mechanism to extract knowledge facts in the patterns by searching the attention graph in language models. This method avoids using expensive label data in supervised learning or listing complex syntactic rules in rule-based extraction. The first step is to process and prepare each sentence of the abstract into a list of tokens, and then noun-phrase and phrasal verbs are recognized and combined. In order to find the listed relationship between the knowledge triples instead of listing syntactic rules, we are going to use the attention mechanism in the first to extract the relationship between words. We will illustrate how attention is calculated and what attention should look like to give you an understanding of it. So firstly, the input token x1, x2, x3 is transformed into a sequence of vectors a1, a2, a3, a4. Then each vector is transformed into a query vector and a key vector by the linear transformation. Start with the query vector q1 here. For example, the query vector will have a dot product with the key vector k1, k2, k3, and k4. Then softmax is applied over all the scores, A11, A12, A13, and A14 to normalize them to be positive and sum to be 1. Then the attention score with a cap here decides how important it is when referring to the query vector. So after the calculation, the attention graph or the attention matrix will be obtained like this figure. We will use a beam search to find the best knowledge triples. So take the sentence, the magnetic force provided levitates the shaft as example. The head-tail pair here is the magnetic force and the shaft. The beam size equals to 2. The search computing process are as the following. First, instead of searching forward, the searching algorithm is searching backward. We need to add the tail, the shaft, to the beam, mark the head, the magnetic force as the ending position, and initialize the attention score as 0. Second, find the token with the largest attention score with the tail, the shaft. You can see here is the levitates, and add that to the candidate. So now is the shaft and the levitates. And update attention score to 0.7761. Mark the token levitates as added to prevent search again. Then find the attention score between the relationship levitates and the magnetic force. Here is 0 is this. And the total attention score here is 1.257. And thirdly, similarly, the search will calculate the second largest candidates because the beam size is 2. We need to find 2 candidates, which is provided in between, and the result is 0.5838. The search will be stopped again, because the number of candidates has reached the limit of beam size 2 and also reached the marked ending position, the shaft. The 2 candidates now both have the attention scores from tail to relationship and relationship to head. The candidate with the highest attention scores, here is the magnetic force, levitates the shaft, will be kept and returned. So using the method, we processed 457,000 patterns. This is a quantifying character on the whole. We also had an evaluation on the existing entities we extracted. We built a standard list of mechanical engineering related technical terms as a benchmark to test whether it is covered in the database. We choose 3 subcategories belonging to the mechanical engineering and totally 180 corresponding terms. So our pattern knowledge graph is compared with 4 other methods, including WordNet, ConceptNet, B-Link, TechNet. The results are listed in this table. You can see the pattern KG reaches the highest recall rate here and is doing well in all subcategories. We also had an evaluation on the relationship we extracted. We built a standard list of mechanical engineering related relationships as a benchmark to test whether it is covered in the database. There are 5 publicly related engineering datasets published before pattern KG. However, some of them don't have semantic relationships, for example, B-Link or TechNet, or some of them is a linguistic English dictionary, which mostly provide the taxonomy semantic relationships. So it is unfair to have a quantifying comparison between them. Only the result of pattern KG here is computed, which is 0.67. So in summary, so far for our research program, we have proposed an unsupervised method to construct the pattern KG. We conducted a quantifying and qualitative analysis. The comparison result is showing a good result. So with our unsupervised method, we can build a large size knowledge graph, which also has an ideal quality. This is a basic step toward our next move, computational creativity, to generate idea automatically. Thank you.
Hi everyone, my name is Yinshuang, a third-year PhD student from the University of Texas at Austin. Today my presentation topic is Information Retrieval and Survey Design for Two-Stage Customer Preference Modeling. Before the presentation, I would like to thank for the contribution from each author. I would like to start with the background and motivation of our study. Given that the customer's purchase decisions are affected by varied factors, customer preference modeling can be used for predicted demand and address customer needs, which is critical to guide manufacturers and designers to develop marketing strategies and optimize the product configurations. Here is a typical example of the network-based customer preference model. This model can comprehensively consider multiple information, such as a social relationship and customer decision-making in different stages. However, one essential limitation of conducting such a comprehensive study is the data availability. It can be represented as that some of the existing data are lack of synchronized social network data and customer choice data. What's worse, because of commercial value of customer preference data, there are few public databases exist for customer preference modeling. To this end, our research objective is to develop a systematic approach that combines information retrieval and survey design in support of data collection for customer preference modeling. Specifically, the collected data should support collecting social network data and customer preference data simultaneously and support customer multi-stage choice modeling. Next is an overview of our approach. It involves 4 modules: product database establishment, 2 modules in survey study design, and survey data collection. In Module 1, we construct a product database and collect product features that will be used in the survey. Then, before designing the first survey, we introduce a pilot study to test whether people can have clear memory on which product they have purchased and considered within different time periods, such as 1 month, 3 months, or 6 months. If people have solid memory, we can design the first survey to get the customer purchase experience as their reviewed preference. Otherwise, we may need to design a choice experiment to get customer's stated preference. Finally, with survey design and several rounds of tests, we publish the survey on a crowdsourcing platform to get the responses. Next, taking household vacuum cleaner as a case study, I will introduce more details about these 4 modules. This page introduces our works on Module 1, which started with using web crawling technique to collect 5 common types vacuum cleaners information and customer reviews from mainstream online shopping platform. Then, based on information feature mining techniques and ranking the feature presenting frequencies, 22 frequently discussed features identified. Finally, we obtained an output database including 1,170 product data. Next is how we design the customer purchase memory test. As shown in this framework, we start with asking participants whether they purchased a vacuum cleaner within the past 2 years. If so, they will be asked the exact period for their purchase, and then provide the model they purchased and considered. Any times when they give a negative answer, the survey will end. In order to reduce participants' workload, we design a user-friendly interface to help participants find their purchase and the considered product. There are several functions being used. For example, the search bar with autofill function, the quick view function that can quickly show some feature of each product. Here is the result of customer purchase memory test. This result gave us much confidence to collect participants' reviewed preferences if they purchase a vacuum cleaner in the past 6 months. Next is the design of our first survey. It is started with a filtering question to ensure that only people who purchase a vacuum cleaner in the past 6 months can enter the survey. Then, main content of the survey can be divided into 3 major parts. The first part is to collect a participant purchase and consider vacuum cleaner as well as the factors that influence their decisions. The second part is to ask their social network information, include people from their general social network and the ones with whom they specifically discuss the vacuum cleaner purchase. The last part includes a question about participants' personal viewpoint, usage context, demographic information. Besides the filtering question, we also design other mechanisms such as attention check question to ensure our survey quality. The survey was conducted over a 2-month period, and a total of 1,011 complete responses were received. To evaluate the data quality and utility, we conducted a descriptive analysis on the survey dataset, including identifying average profile responses, a summary of usage context, identifying the most popular vacuum cleaner type and brand, important feature affecting participants' decisions, summary of their social network. Finally, we also realized the co-conservation network and choice network visualization. Because of the time limitation, I did not go into details of this part. If someone are interested in this part, please feel free to check the results in our paper. Last is a short summary of our contribution and future research direction. Our contribution are that we developed a systematic approach that combines information retrieval and survey design in support of data collection for customer preference modeling. We developed a web-based survey platform that supports interactive information retrieval and virtual online shopping. The survey supports collecting customer social network data and their preference in a unified framework. The collected data will be made available to the public for broader impact. Our future work will be refine survey questions to dig more detailed social network information and demonstrate the utility of the data in customer preference modeling by performing network-based modeling work. This is all my presentation. Thank you for your listening. If you have any questions, please feel free to contact us.
Hello everybody, and welcome to the presentation of the paper Planning the Analysis of Use Phase Data in Product Planning. This paper was written by Ingrid Wiederkehr, Christian Koldewey, Roman Dumitrescu, and myself, Maurice Meyer. The presentation is structured as follows. First, I will introduce you to the topic. Then, I will present the developed method. Third, I will give you an application example of the method. And fourth, I will derive 3 conclusions of the paper. In recent years, we have seen a lot of technological progress that led to drastic changes in a lot of areas. For example, in the product area, we have seen the transformation from mechatronic products to cyber-physical systems. These systems are able to collect data during their use phase and to send it to cloud platforms with their connectivity elements. In the analytics area, we have also seen transformation. In the past, we were only able to analyze few data sets with classical methods of statistics like the regression. Now, in the big data era, we have seen a lot of advances in data analytics and AI and are able to analyze huge amounts of unstructured data. Lastly, we come to the application areas, for example, product planning. In the past, this was mainly assumption-based, and assumptions were needed to improve products. The information sources were workshops and interviews with clients. Now and in the future, we're talking about data-driven product planning. So we use use phase data to generate insights about our products and to prepare fact-based decision-making. But how does this data-driven product planning work? Let's have a look at the main principles. Let's assume that we currently have a product in the field that generates use phase data. And let's also assume that we want to develop a future product that, of course, is an improvement to the current product. We can now look at the old and new product planning uncertainties, for example, assumptions that we made in the product planning phase of the current product, or questions that we now have in the product planning phase of our future product. With the use phase data, we can analyze these uncertainties and, in the best case, eliminate them. This gives us new insights about the use phase that we can use in product planning to develop the new product generation based on facts instead of assumptions. In our paper, we focused on the early phase, the planning phase of data-driven product planning, and we addressed the research question of how to successfully plan the analysis of use phase data in product planning. For this, we developed a process model with 4 phases. The first phase is the identification of investigation needs. In this phase, we identify pains and gains of key stakeholders, evaluate and prioritize these. In the second phase, we analyze the data analytics capabilities. Here, we evaluate 3 dimensions: the product, the customer, and the company. In the third phase, we define boundary conditions and goals. This phase is based on the first and second phase. So we define the goals and success criteria for the investigation based on the investigation needs. And we specify the boundary conditions of the analysis, which is based on the analytics capabilities profile. In the fourth phase, we specify the use case by deriving questions with the question canvas, by prioritizing questions, and by specifying the necessary data. This gives us the use case profile, which is the result of the method. Now I want to quickly show you how to apply the method. This example is with a manufacturer of ATMs and retail machines with about 10,000 employees worldwide. The ATMs of this manufacturer are installed all over the world. Here you can see a portfolio that looks at the strategic relevance and the associated uncertainty of the identified investigation needs. The upper right corner is especially important, as these investigation needs have a medium to high strategic relevance and also a medium to high associated uncertainty. On the following slides, we'll focus on the high reliability that for the manufacturer has a very high strategic relevance and a medium associated uncertainty. In the second phase, we looked at the data analytics capabilities profile. Overall, as you can see, the company has a high or even very high data analytics capability. Only the determinacy of the product behavior was considered to be very low. This is because of unstable environmental conditions of ATMs. For example, the paper of the banknotes is quite different in different countries, and the ATMs have to cope with every paper, with every banknote. In the third and fourth phase, we derive the following use case profile. In the upper half, you can see the goals and the boundary conditions. The goal is, for example, to identify the most serious causes of failure. A boundary condition is, for example, the consideration of environmental factors. In the lower half, you can see how we specified the use case. We used questions, for example, after how many runtime hours do the reels break? And we also included the necessary data to answer the questions. Here, for example, the EEPROM, the service reports, and the ticket system data. This use case profile summarizes the results of the earlier phases and thereby clearly lays out the analysis to be performed by the data scientist. Finally, I want to draw 3 conclusions. First, analyzing use phase data and product planning offers a significant potential to plan new product generations based on facts instead of assumptions. Second, the use phase data analysis must be systematically planned to extract valuable insights from the data. The presented method addresses this need. Third, the presented method was applied with 4 manufacturing companies with very different data analytics starting positions. In all cases, we were able to plan analysis that are now pursued. Therefore, our method proved to be valid. Thank you very much for your attention. I'm looking forward to answering your questions.
Okay, thank you all for your presentations that were really interesting. We have some questions on the chat, and therefore I will read the questions for you. They are mainly for the second presentation and the fourth presentation. I will ask to be short so that we can have at the end also some time for some question for the other presenters. Okay, so the first question is for Xiao. Can you give us more precise idea about your plan to apply the outcomes of patent searches with your innovative approach? How do you expect that patent data can shed a light on designers' behavior? Xiao, you can answer. I don't know. Perhaps he isn't here, or he had some problems with the micro. So we can pass. Another question. Meanwhile, I hope that Yang can join us again. The question is for Yinshuang Xiao. Do you think your approach can also be effective for products where the buyer and the user are two different subjects? If no, what would you change to adapt it?
Sorry, could you please repeat the first part of the question?
Do you think this approach can be effective for products where the buyer and the users are two different subjects?
Yes, I think our approach can applicable for this kind of situation because our survey is published for all of the respondents in the crowdsourcing platform, and in the platform, I think there have different peoples to attend our questionnaire, our survey. So I think it includes people from different education level or income level, and also maybe have different purchase preference. So I think, yeah, our survey poll is a very general.
My question was also similar and was, have you already thought about the possibility of integrating data from users collected directly from system? So not only customer data, but also user data.
User data. I think, yeah, I think in our survey we didn't specify whether. Oh, I think our survey is mainly for the customer who purchased the product, for example, in the past 6 months. So I think this is mainly for the users. They have the, for example, the vacuum cleaner, but not for some.
Thank you. We were thinking just because sometimes needs arrive from purchasing, sometimes else needs arrive from use. And therefore, it would be interesting integrating the two parts of the process, okay? This. Okay, now we can hear you. So there are some questions for you. Okay. The first is, can you give us more precise idea about your plan to apply the outcomes of patent searches with your innovative approach?
Okay. Thanks for Nico's questions. And for the first question, we just did a systematic literature review, not a patent search. So we did this systematic literature review to review the overall structure of the patent for design studies, and we can see patent data contain many useful design information and can be utilized or mined for design support, including design theory, design methodology, design tool, and design strategy. For example, several studies have shown that using transformer like GPT can, in conjunction with patent database, can help designers automatically generate some innovative design concepts. So I think this is a very interesting directions to follow. And for the second question about how to use patent data to shed light on designers' behavior. I think patent data contain many innovation activity footprints and collaboration information of inventors and organizations in the bibliometric information of patents. So we can mine and analyze this data to get insights about the designer's innovation behavior at high level.
My question really was similar, because you analyze obviously patent scanning activities, mainly looking at the information and the aid that you can provide to designers. Okay, but the algorithms that you see promising could be also useful to analyze the distance from patents, because sometimes there
you mean
distance from paper, among paper, between patents.
Okay, I think these algorithms can not only apply to patents but also apply to papers, and we can
patents. But usually when you do patent scanning, you don't look just the contents within the patent, but also the distance of the patent with other patent. Distance.
Yeah, distance.
There are some words in literature that analyze the distance between patents. So my question was, if your algorithm could be also useful in this sense or not.
Yeah, I think the answer is yes. The distance among patents, also the knowledge distance. Yeah, we can use this knowledge distance to analyze the field or similar things.
Okay, thank you. Then there is another question again for you from Maurice. And the question is, in which phases of product development process can patent data analysis be used best? For example, it is more suited for the early conceptual phase or for the late phases detailed design?
Yeah, I think this is a very good question. And I think patent data is more suited for the early stage design, also the conceptual phase. Yeah, because patent data contain many design information to assist designers to generate more innovative ideas. For example, Haoyu's patent KG is a very outstanding work and a very good example. We can use the knowledge graph based on patent database to develop some intelligent algorithm to generate design ideas. But for the detailed design, we still need some effort from the designer's end.
Okay, thank you. Another question for you, but from Vanya, that asks, did you consider a broader context of trees in your data search, such as trees contradictions?
Yes, I have already included some trees-related studies in my review paper. For example, I reviewed a work that the authors use the trees, use an algorithm to automatically extract trees contradiction matrix from patents to simulate novel solutions to design problem. You may check more details in my paper. Thank you.
Thank you. Then we have a question from Niccolò to Maurice. And another from Iryna, again to Maurice. What do you think are the main barriers for the adoption of a data-driven culture in companies?
Yeah, thank you for this question. That's a very interesting one. I think that many manufacturing companies, especially, are well established, and they have been successful for many years, and also successful before analyzing data. And because they were so successful, many employees do not see the need to analyze data in their daily business. We saw this in an own interview study that we did with manufacturing companies, where some companies told us that they provided their developers tools for using AI and so on, but these developers didn't use them because they said, well, I have tackled these tasks in the past with other methods, and why should I use this now? So in my eyes, the people need to be convinced by showing them clear benefits and an added value of analyzing data. And this could be done, for example, with pilot studies with small projects that address serious issues. And if you can show the people that you can solve these issues with data and create an added value, then it will be possible to convince them and also to create a data-driven culture in the companies.
Okay, thank you. There is another question from Iryna, and then I have one mine. When you plan to collect data, how do you deal with data that you can keep as additional but not mandatory?
Here I would start to say that you can distinguish two approaches for analyzing use case data. And the first one is a top-down approach. This is the one that we also use. So you come from the goals and from your objectives, and from these look at the data that you need to answer, for example, the questions or to test the hypothesis that you created. The other one would be to use the bottom-up approach, where you first look at your data, see the data that you have available, and then then think about what you can do with it. But we used this top-down approach. So we derived our data from the goals and from the questions that we used. And then we only gathered and analyzed the necessary data. So the additional data was not utilized, but only stayed in the cloud or some other memory.
Okay, thank you. Then I have one from me. Have you thought the possibility of use this data not only for supporting design decisions, but also for analyzing behaviors in order to provide users with hints or advices so that they behave differently?
In our work, we did not focus on this.
No, not in this work, but it is something that you could consider, or
Yes.
it is something too far from what you are considering?
Well, I think this goes a little bit into the topic of smart services, where you analyze data and then, for example, provide people with suggestions or with additional services. And this could definitely...
They could be also suggestions for using better the system.
Yeah,
So,
I think this could be possible, but then you have to implement the analysis and the the suggestions online in the product, so that the product is always analyzing the data online and then is giving the user the answer or the suggestion right away. For our approach, this online analysis is not necessarily is not necessary. It could be done online, but we could also gather the data when it is from the past and then analyze it later, and then just see how the user, for example, performed certain tasks or what the product did during the operation.
Okay, thank you. Then there is a question from the third paper. UZ, right? I don't remember your name, sorry. It is from Yinshuang Xiao. Did you also compare the computational efficiency of different approaches?
So this is a very, very critical question. So I actually didn't consider about this aspect about the computation efficiency. And I think I'm going to think about that. And so because of the size, the page limitation, so we actually did some other kind of qualitative analysis. For example, so it's about the accuracy of the extraction of the entities of the tails and the accuracy of the relationships. And we also labeled around 200 patent data, including around 6,000 entities, and to do the analysis work. So if you're interested, we can have a discussion later. But the point, the aspect you refer to is very critical. Thank you so much.
Thank you. Then there is a further question for the second paper, but I would like also to have a question for Iryna, that is the first paper. Then we will pass at this last question. Iryna, mainly you analyze data from research, okay? So you are a step back with respect to design data, and therefore you build a research data management system. So my question is, the data that are centralized in your research data management system could have an impact then on the further activities, so could have an impact also on design?
Thank you for your question. Of course, our data will have impact of design, but we are talking about some research data management system for some collaborative project, which should be active, I hope, during 12 years. And now we are in the second year, and we now make some base for this future research. In this step, what is important for us to correctly use domain-specific vocabulary to describe all data with help of this domain-specific vocabulary and make a semantical connection between all data. So we use vocabulary, we use metadata, we make connection between data, and of course we use already some first queries, so Sparkle-based queries, and in the future we plan that to our approach we can actually feel free us to formulate different type of Sparkle query and receive different type of information which we can use also for design or for analyze of activity of our research.
Okay, thank you, Iryna. And now there is a further question for the second paper, Xiao. So it's your turn again. Now I will read completely the chat. Thanks, Shuo, a very comprehensive work, because I noticed that you also have some other work on patent data. I'm wondering, do you have any concerns about the legal risks using patent data, like infringement, or any ways to circumvent the potential issue?
Yeah, this is a very good question. And using patent data would truly involve legal risk.
Sorry,
Therefore,
sorry, this was just the issue why I asked you about the distance among patents.
Okay, yeah, I got you. Yeah, so therefore some researchers propose some methodology to avoid patent infringement. That is also relevant to trees. So I think maybe we can use some AI or data science technologies to develop some module like design evaluation to evaluate these risks. Maybe we need to have some experiments to test.
Okay.
Thank you.
Thank you. I don't know if further questions are in your minds. You can write in the chat. Otherwise, a question for you, a general question for all of you, because we are considering research data, we are considering patent data, we are considering customer data, okay? All these kind of data, I think, and I suppose, are used to aid design decisions, right? To support design decisions. So I'm thinking about patent data, for instance. They are used for functional analysis, for the investigation of functions, the investigation of technical aspects of system, investigation of possible solutions, or also to investigate, as we were discussing 1 minute ago, also the competitive solutions. Okay, users' data or customer data are mainly data that derive the needs, derive the behaviors of the users, derive the possibility of the usage. Now, if a general question for you, do you think that also data from production and therefore from the industrialization phase, because mainly we have analyzed data from the early phases of product development, and now I'm wondering, just because here we are here to discuss, if do you think that also data from the last phases, so for instance, the industrialization data, the data from production, could be support design decisions? Go, Iryna.
So I think it's really important question, and I'm sure that, for example, production data can support design decision, because production data or manufacturing data should be analyzed, and maybe we should try to become some dependence between mistakes or problems in production phase and in using phase, for example, because I see directly connection between these two art of data in globally. So in any case, for full decision in design phase, we need not only usage phase, but data from usage phase, but in any case, data from production phase, for example, and from recycling phase. So I think all art of data are important. Also, in case if we design some new generation of product, of the basis of all generation of products. So we should analyze all art of data, not just from using phase, I think.
Maurice?
Can I also add to this? Yeah, I would like to add to this that I think it were Porter and Heppelmann who also said that the analysis of data becomes like most valuable if you combine a lot of different data, and this is what Iryna just said. So, for example, in design, it's not only the question if the product meets all requirements from the customer, but it also does or needs to meet the requirements of production. And for this, we need to combine different types of data, production data, use-based data, recycling data. And if we do this, then we can really create products that are optimized in many different ways.
Thank you, Maurice. This was just the point. So the possibility of an integration, the possibility of integrating. Yinshuang?
Yeah, I want to add one more point is that I think the production data, I can say one problem is maybe how to collect this kind of data is very different from, for example, we collect the customer's data, we can use a survey. I think maybe for the production data, for example, during the manufacturing, maybe we need to use some sensors, different technology to collect the data, I think.
Yeah, sure. Is it possible in your mind an integration to either design decisions?
Yeah, once we have this kind of data, I think it could be guide the designer to say whether have more efficient ways to design, for example, the structure of the product and then more efficiently produced in the factory, maybe.
Okay. Okay. Auzi?
Yeah, so can I add one more to this? So I think the data from the production at the very end is kind of like the pattern data. So being very like descriptive and contain very, very like detailed information. And so the answer is definitely yes. So because how to apply data is actually depends on people. So as a question asked, there are several phases in the design process, a very early stage, a middle, or like late stage. And so for the early stage, we can like use the data combined with the machine to output some like very set random or say generative result. And for the late stage, we may like need the people involved, the human in the loop design. So the question is about actually, it's more about we need to consider about how to use the data by people or just by human, by machine. So the data are always being valuable. So it's about how to use that data.
But do you think that some production data of previous products could be useful also in the early phases of the next ones?
Sorry?
I was wondering also if production data of previous products could be useful in the early phases of next products. This was because often it happens that you have different versions of products or you have different families and they share some parts, right? And also some production phase. In any case, it was just an idea. So how many data we can integrate and for which kind of uses?
This is a very critical question. So
I don't know, Shuo.
Yeah, I think you mean we can use some early version of product design to help designers to better develop their design outcome. I think there are some studies like case-based reasoning. We can use some earlier design solutions or earlier version of products to make some reasoning to in the later design or generate some new iteration for to meet the design requirements. So the answer is yes, we can use this previous product, and I want to I want to say we can also use some data generated in the design process. For example, we can log their design process in a more structured way, like, for example, how designers generate their idea in what situation or what environment. Then maybe we can better understand the designer's design's behavior or better understand the whole process to generate innovative ideas.
Okay, this last question was just for reflecting on the possibility of integrating our work with the one of others that are working in different direction from the own direction, but it could be valuable also the collaborations with colleagues that look at different data from the ones that we are looking on. So I don't know if further questions are present. Otherwise, I think that we have to leave our session. We have to conclude. Is there any question? No. So I would like to thank you guys for your contribution. All of them were really interesting. I wish you the best for your research work, and I hope you can enjoy the last part of the conference. Okay, so bye. Thank you for this session, and see you at the next conference. Okay.
Thank you,
Goodbye.
Francesca.
Bye bye. Bye bye. Bye bye.
Thank you all.
Bye.
Bye.